So this is the second part of this section 1.3 of Griffiths' book, Quantum Mechanics, third edition. The section 1.3 is probability. The second part that this video is about is the subsection 1.3.2, which is about continuous variables. So in the previous video, we talked about discrete variables, and now we are talking about continuous variables. Okay, but let's go by analogy. So when we are talking about discrete variables, we talked about the probability. So we are talking, for example, the probability that someone was aged 14 years old. So probability of having this discrete variable j. When we are talking about continuous variables, instead of this notation, we are going to use this other notation, rho of x, with the idea of having the probability of having this variable x, a certain value x. But since we are talking about continuous variables, you cannot precise exactly one value of x. Now, we talk about ranges. So the way to go is, if this range is infinitesimal, we use this, meaning that this is the probability that x is between probability that our variable, let's make it like this, the probability that the variable is lies between x and x plus dx. If we think about finite range, which is usually what we compute the probability with this integral. So the probability that this quantity x lies between a and b is obtained with this integral. Okay, so this is the probability that the variable x lies between a and b. Okay, in this range. Okay, so this is our analogy between discrete variables and continuous variables. What else did we talk about when we were discussing discrete variables? We said that the sum of all probabilities have to equal 1. Well, now that we are talking about continuous variables, what is the equivalent of a sum? Okay, so now we don't talk about sum anymore, we talk about integral. Okay, so the integral of this probability density, so this, we call it probability density, the integral of this probability density should be 1. Okay, so the sum here we had put from 0 to infinity in the case of ages. The integral here, we are going to put, for example, from minus infinity to infinity, covering the all possible range. When we are talking about expectation value of mean or average, what was the notation that we used? This one. So the sum of each j with its corresponding weight, with its corresponding probability. So we put this sum like this in the case of ages. What is going to be the equivalent now for continuous variables? Instead of sum, we have an integral x weighted by this probability density, right? From minus infinity to infinity, and we'll be using the same notation like this to denote mean. Okay. Continuing, we said, well, this is the mean of j, but we can compute the mean of any function of j, like this. Well, same story now for the continuous variable. Any function of that variable will be obtained by solving this integral. Okay. And finally, we talked about variance. We said that the variance could be, we found an equation for the variance, which we wrote like this. Well, the same thing is true here. The mean of x squared minus the square of this mean. That's the idea. Now, you see that in this course, we'll be computing mean values, we will be computing variance, standard deviation over and over again with continuous variables and with discrete variables. So you see that knowing how to solve integrals, of course you already know, but integrals will be used a lot in this course. So the first problem that I'd like to suggest that you play with or try to solve is the problem 1.3. I'm going to make a video for this problem as well, but this is very, 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 very important because the distribution that this problem works with, this probability density that we play with, is a Gaussian. Okay? Is a Gaussian distribution, and we will be playing with Gaussian distributions over and over again. So I really suggest that you try to solve this problem, but I'm going to make a video for this problem as well.